In this video, we are going to discuss Section 5 of Chapter 12, Reaction Mechanisms. Here is our learning target for this section. We're looking at reaction mechanisms and intermediates. So what is a reaction mechanism? It's a series of elementary steps that are going to describe our chemical reaction. In this series of elementary steps, intermediates are formed, and they are reacted in a subsequent step and do not appear in the overall chemical reaction. So if we look at this reaction right here, we can see that a mechanism that is composed of two steps has been proposed. In step 1, we've got NO2 and NO2, and then we get NO3 and NO. The blue spheres represent nitrogen and the red spheres represent oxygen. So then in step 3, this NO3 appears again. That is an intermediate. It is something that is produced in step 1 and is reacted in step 2. You can also see we've got our carbon monoxide, CO, NO2, and CO2 are produced. We can also cancel out this NO2 with, say, this one, and you can see what is left is the overall chemical equation. We've got our NO2, we've got our CO, we've got our NO, and our CO2. This proposed reaction mechanism that is composed of two elementary steps does give us the overall balanced chemical equation that we are looking for. So it is a possible reaction mechanism. Reaction mechanisms can never be proved absolutely, and there could be other mechanisms that are possible for this chemical reaction. More experimenting would be necessary. So the reaction mechanism that we just looked at had two elementary steps. Elementary steps are reactions where the rate law can be written from its molecularity. And molecularity is the number of species that must collide to produce the reaction indicated by that step. A unimolecular step is a reaction that involves just one molecule, and that will be first order. A bimolecular step is a reaction that involves the collision of two species, and that will be second order. Termolecular involves the collisions of three species and will be third order. This is very rare because all three species would have to simultaneously collide. This table summarizes the types of elementary steps, the molecularity, and then the rate law that results. Notice for bimolecular, you have a couple of options where it's two of the same reactant or two different reactants. And the same idea applies for termolecular, two reactants or three reactants. The elementary steps in a reaction mechanism occur at different rates. In fact, each elementary step has a different rate constant. So the step that will determine the overall rate of reaction for the reaction mechanism is going to be the rate determining step. So a reaction can only proceed as quickly as its slowest elementary step, and we can write the rate law from the molecularity of the rate determining step, the slowest step in the mechanism. This funnel is an analogy for the rate determining step. The rate at which the colored solution enters the flask is determined by the size of the funnel, not by how fast the solution is poured into the funnel. So if we're looking at a reaction mechanism to describe an overall reaction, it has to meet these two requirements. We have to take the elementary steps and add them together, and it must give us the overall reaction that we're looking for. And then the mechanism must agree experimentally with the determined rate law. In previous sections of this chapter, we talked about how to experimentally determine the rate law. The rate law for the rate determining step must agree with that rate law. So here you can see an overall reaction that we are interested in looking at. It's experimentally determined rate law, and then a proposed reaction mechanism. If we cancel out this fluorine atom intermediate, we get the overall balanced chemical equation that we are looking for. 2 nitrogen dioxides, a fluorine, and then 2 of these NO2F molecules. So that's one requirement of looking at a reaction mechanism to see if it could work for a given reaction. The other requirement is to see if the rate law of the rate determining step matches the experimental rate law. The first elementary step is the rate determining step. It is bimolecular. It has 2 species that must collide in order to react. And so its rate law would be, this matches the rate law that has been given. So that's the second requirement in determining if a reaction mechanism could possibly work for a given reaction. This concludes our video on reaction mechanisms.